Yeah, you can see the.
So guys, we just sent out the slides for the session as well as some commands that need to be run before starting this session. Right, so we come to that slide again here in the middle, but we put it on the Slack channel so that you can connect to the cluster. So you won't be running the Kubernetes cluster on your machine locally. We have cluster set up for us by Shambhavi and Arjun here, who are students at IIT Delhi. So we access that cluster and use that cluster for running our commands today. Right? So make sure you have the commands that we've pasted on Slack running on your machine. Okay? If you're facing some issues, call the guys standing in the back. Trouble them today in this session. Okay? Right? Yeah, first. So, as we spoke throughout the day, right, that Docker is used for running your containers on a single node, right, single machine. But when you're running, you want to run your application at a cloud scale, a single machine tool won't work, right? So you need something to scale it at a cloud infrastructure level. And you need someone to easily manage scaling of these containers, manage if it goes down on the demand, creation of the container if it goes down and all that stuff, right? So Kubernetes is an orchestration framework that's used in cloud environments to manage deployment of the container in the cloud infrastructure, right? So uh, there are multiple components involved in the cloud Kubernetes infrastructure. The first, there is a control plane, and there is in the control plane is where all the brain or all the processing that's required for Kubernetes runs, and that runs on what is called as the master node of Kubernetes cluster, right? And along with that, wherever your applications are running, that the containers running your applications are running, they are called as the worker nodes in the Kubernetes cluster. Right? So what you have in the control plane of Kubernetes is the API server. Yeah. So what you have in the Kubernetes control plane is this API server, which is what you actually connect to when you run the kubectl command, right? That's where it gets hit, the request hits when you run the kubectl command, right? So whatever command you ran right now actually went to the kube API server in the cluster that we have locally running here, right? So after that, there is another component that is called as etcd. Right, so as we said that it's used for managing, Kubernetes is used for managing large infrastructures where there are multiple worker nodes running, where there are your containers running on these worker nodes. Right, so all this information about whatever image these containers are using, what network they are connected to, what kind of volume or what kind of storage they want, all this needs to be managed somewhere centrally for all the entire infrastructure. Right, so you need to store all this information somewhere, and etcd is the central key value store that's part of the control plane of Kubernetes, which helps store this information. Right? So the third component that involved is the scheduler, where as you said, now when you had a single node, you could just spawn, like when you do a Docker run, that container came up on your machine. Right? But when you have multiple worker nodes running, you have to see if you have 100 containers running, you don't know, right, if you want to run the 101th container, which of the worker node has the resources to run that new container, right? So for that, you need a scheduler to schedule to analyze which of these worker nodes have the correct amount of resources available and spawn that container there. Right? So what does scheduler do is first it filters all the worker nodes which are available and sees which have available resources and then sorts them based on how much resources are there accordingly, which has the maximum resources, which has to be the next choice to schedule the application or the application container on that worker node. Right? Uh, Now, these are whatever we discussed till now were the control plane components, right? So, other component that runs on the master or runs on worker nodes or where your containers will be finally running is a kubelet, which needs to check. So, it needs to see the Kubernetes control plane needs to see, right, if all your all your containers are in the running state or not. And if they are not in the running state, inform you, or if if it can just fix it by restarting the container. That all also Kubernetes support. We'll see how it does that right now. But for that, it needs a local daemon running on each of these worker nodes to see if it's keep check of all the containers that are running on the each of these worker nodes. Right? And we'll see again in a bit tomorrow that there is something required to manage the networking for these applications running as containers on these worker nodes as well. Right? So you must have seen I've been telling container, and there's been this component called as pod here. Right? So what is this pod? Right? So pod. So before we go, and let's go off topic. What is a cell in a living being? Right? Can I get an answer for that? Yeah, the smallest object that's required for a living, the smallest entity, right? That's required. So for anything running on Kubernetes, pod is the smallest entity, the smallest logical entity that's required to be running your application, right? So pod can consist of more than one containers running inside them, right? So it's a single unit of deployment that's part of Kubernetes infrastructure, which can have more than one containers running on them. So then the next question arises is, we've been studying Docker and Docker containers for the entire day. Why suddenly not containers and why pods, right? So the thing is, how the development happened is they had containers running and they wanted to evolve that infrastructure to a cloud infrastructure, right? So you do not want to change the base thing that goes into it, right? So containers, you don't have to modify whatever infrastructure is running for the containers, and something should be able to adopt or add a wrapper over it and still be able to manage it, right? So why we needed a pod was container was able to handle the namespace, the C groups kind of thing. The isolation was able to be handled by container, but you needed some APIs to keep the check of if it's in the running state, if it needs some volume to be shared across cluster, it needs to across worker nodes, it needs to communicate. For that, it needed a wrapper around these containers, and that's why pod was coming into picture to handle easy management of these containers. Right? So pod is the smallest entity, that logical entity that we have in the Kubernetes infrastructure. So as I mentioned that there are, so just let's take a step back from this spotting. Show of hands now, who got these commands working right now, right? I hope major of you have these things running, right? So let's get our hands dirty and get access to this cluster and see what we can do on this cluster. So the first thing that we want all of you to do is create a namespace, right? Namespace, as we have in Docker, is your area of workspace where you can have an isolated environment for your network, your sources, for you to run your pods, which internally run the containers, right? So we have shared the slides, so in case it's convenient for you, and please copy paste these commands from the slides. Right, so the create namespace will create your namespace. Make sure you use unique namespace and don't overwrite it, because we all are sharing the cluster here. Right, you can use your name and college as a namespace name for you.
Yeah, just to add to Priyanka's point, just replace that last entry, right, and use whatever you want. You don't need the brackets. Then.
Yeah, so the brackets are not needed. The bracket is true that it needs to be replaced by something that you want to use, right? Rest can be easily copy pasted.
And just another point to add, this namespace is a Kubernetes namespace, right? Don't confuse this with the Linux namespace we saw in the last session. It is the same concept that I showed you with that GitHub and pip example, right? So here we are all going to have a namespace of your own, and the work you do inside the namespace will not disturb others, right? So when you run things like get pods, you only see your pods in your namespace, right? That's the use of namespace.
Yeah, so if you've created your namespace, you need to set your context to this namespace. This is the name that you gave here. Use the same name, remove these codes, but have to replace this name that you gave to the namespace here as your namespace name, and set the context for your terminal, your machine to use this as the namespace for your Kubernetes cluster, so that we don't go and mess with other namespaces in the cluster. So in that, if you clone the repo, go into the KTest folder there, right? And inside that there is a pod example folder. Can you just go into that folder? Right, so if you are in the folder now, you will see a YAML called nginx-pod.yml, right? So can you run this command that we have here and replace this hyphen n with? It's a bit big, it's still cloning. Okay. Oh, okay, it's cloning. Okay, sure. So if it's you're having trouble cloning the repo, just we've shared the tar file on the Slack channel. You can download from there, and Kavya is sharing the command to untar it and have the folder ready on your local machines. So I see some of you are facing issues running these commands. So make sure that you run your commands in the folder where you've downloaded the the config file, that config environment from Slack, right? It should be running in the same folder. You should have that same path in your terminal when you're running these commands. Otherwise, you won't be able to connect to the cluster.
Okay, so for Priyanka's latest instruction, so you have to run the kubectl command only from the directory where you actually download your config file, right? So that means you have to change this file path. It will not just be .yaml, it will be path to YAML, right? You have to do /kts/ something of that sort. So you have to adjust the file name here after -f to meet your local folders.
So to get the path to this folder, just do, if you're on a Linux machine or Mac machine, do pwd, whatever output you get, copy paste that and replace this with the path to this file. Okay? So if you could run the first command correctly, run the second command and see what you're getting. So what this YAML did was it tried to create an Nginx pod in this cluster on the namespace that you had created. Right? So if you open the Nginx pod Nginx pod.yml, you will see this white portion that we have here. Right? So what it does it says that the name of the pod should be Nginx, and the name of the container that will run inside the pod will also be Nginx, and what image to use, right? The way you had image to be used when you were building the containers using Docker, you have to pass the image. Similar way, you have to pass the image to run the containers inside this pod. So this image is what will give the path to the image that needs to run as Nginx image. And once that's done, you need to tell that, okay, for this container pod, which of the ports should be open to accept connection from outside, right? So we have opened port 80 as we've been running for the Docker container we have been running since morning. So for that, similarly, in the container, Nginx container running inside the Nginx pod, we have container port 80 open to accept connection, right? So if you do the kubectl describe for this pod, you should see this itself running, showing you that this container is created with this port open, right? So show of hands have reached till the describe command. So if you have this container running, now for what we have is a one pod running and a container running inside. But as I said earlier, you should be able to run multiple containers inside a pod as well. Right? So why do you need to run multiple containers? Right? So traditionally, this microservice architecture, we've been telling that you should run one processing unit as isolated container, right? So why do you need multiple containers running inside a pod? So there are two special requirements for it. One is what is called as an init container, right? That can run alongside your main container that does the processing. So why is it required? Suppose you have a microservice chain, right? So if you have a front end running and there is a back end running which is running your Redis or some database, right? So the container, that front end should come up and open the port. Once it opens the port, that means it's ready to accept requests from clients, right? So it should be ready to open the port and accept requests only when the database in the backend is up and ready, right? Otherwise, it should not be accepting requests. Otherwise, these requests are going to fail. So there is kind of a dependency between the front end running till the backend, till the memcached or your Redis or your any backend database running, right? So it should only run when this has come up. So this, to maintain this kind of order in which these pods need to come up, you can use what is called as an init container. Where what will the init container do is it's a run to completion container. So it won't be up all the time. What it will do is it will come up, keep checking that if the you have to set what command you need to run inside the init container. So what it will do is generally all these microservices open an endpoint, right? So it will keep checking if the DB pod is up and exposing or handling requests on whatever ports it's supposed to do. So once that is done, then it knows, okay, this pod is up, then I'm okay to run my front end now. So what it'll done is it'll start initializing the pod, and once the pod comes up, it'll kill itself. Right? Init pod will go down once your application pod is come up. Right? So this is a short-term container just to keep the check of suppose your backend DB is up or suppose you're creating a volume, its volume is created or not. Sometimes in a cloud infrastructure, you have shortage of resources or it takes time for the volume to come up. So in such cases, when you have some resource allocations happening, you need to wait for them to come up and then only your pod should start. So init handles that. Another use of multi-container is what is called as running a sidecar. So we'll cover it. Why do we need sidecar for networking in much more details in the tomorrow session. But what sidecar does is sidecar is not a run to completion pod as init pod. Run to completion container as init container. What it can do, what are major applications of running a sidecar is if you want to do some monitoring for your application or some log collection for your application. You don't want that to be part of your application. You can run that as a sidecar because what happens is when you have a pod, right? So go back to the figure. When you have a pod, these containers that are running inside the pod actually share. They are kind of, you can assume this as a single machine kind of unit machine that's running. So these containers can access each other locally. So if you ping local host, suppose you had some sidecar running, which as we will do in our example, if you had a sidecar running with your Nginx container, if you have pinged that container, you should have it at local host because assume they are on the same machine running as different processes that way, right? So they are as they are access multiple processes across in the same machine. Similarly, you can access multiple containers within a same pod. It's like a local environment for them, right? So that way, what it promotes is you can have, because it's kind of a local environment, these sidecars can be used to monitor whatever packets are going on, whatever requests are coming in on that application container. Right? So whatever processing which is not application-based processing can be can be running as sidecar as well. Right? So these are the reasons that you need multiple containers per pod. So this is an example you tried. These are set of commands that you can just try. I'll give you a few minutes just to try and explore what is there. But the first command in this list that I want you to try is this last one, which is checking the running containers in a pod. So you have the Nginx pod up, right? So you need to check if it's actually running, right? So if you want to list what are the containers that are running in a pod, you can use this command to get the list of containers running in the command. An easy way also to check is instead of using this command, is the first command that you ran is kubectl just get pods and it will show. The output should show at the end there will be a 1/1 running, showing that okay, you try to start one container in that pod and that's up. That one implies this one implies what are the number of containers you tried switching on, and there are a number of containers that are on in that pod, right? So now it will be one on one. The next example that we'll try will be with a sidecar, and then you will see that you'll have a 2 of 2 running as when you do kubectl get pods, right? So it's just to keep a immediate check of if the containers are up in a pod, and using the last command you can see the name of the container that's running inside the pod, right? So you can do that, and I guess rest of the commands just keep it handy. And when you move ahead and if you want to debug something, you can use this log command just to check what are the logs that are getting printed for your container. I suggest not running the rest of the commands as of now. We'll instruct on what to use when throughout this session. Yeah. Okay, so if you run this command, we can, in case you get time to try these commands again later. The next thing that we're going to try is running 2 containers in the same pod, right? So as we said, it's a local environment. Let's test it if it's really a local environment, right? So in the same pod example folder, there is another file called as shared volume.yml, right? So the same way as you applied the older nginx pod.yml, please run the same command as we've shown here. Obviously replacing the namespace with the namespace of what that you have created. Run this shared volume container. So what this basically does is it creates a volume that gets shared across these containers, right? So how do you see that? If you open this shared volume.yml, what it has is that first we create a volume which is an empty directory. Empty directory means the node on which your container is getting created, it creates an empty directory there which will be mounted as a volume, and this volume can be shared across these containers in the pod, and they can be mounted to different locations on the pod, right? So first nginx pod that you have mounts it to the user share nginx HTML location, and the other one that's running along with this nginx pod, nginx container, mounts it into the HTML path, right? And what it does is it actually, we want to test if it really is being able to share it, right? So what we do is in this in this other pod that you're running, we actually write the date into this file that's getting in this folder. And we try to, and in the next thing, we try to see if we are able to get that file and read that file in the nginx container, right? So once you run this first apply command, you want to get inside this container, both of these containers, and check what they've written or what they are reading, right? So the first container, this is the second container which is writing the data, right? So you can exec into both of them. These can be run simultaneously, and you can see that both of the output of both these commands should be same, right? So this second command has written the date. So when you do a cat here inside the container, it is able to read the date, write the date, so you can see the date. And the same thing you can see it here, that you are able to read the date in this in the nginx container, right? So I didn't mention it in the last slide, but exec is the command that you use similar to what you use in Docker to get inside the containers and explore its directories or explore what's running inside the container, right? And what it implies here is the nginx shared is the pod name, right? And -c. Here it implies that this is the container they name inside the pod that you want to exec into. And after that is the command that you want to run, right? As we did, like some of you, we tried was, we just want to get into the shell of that container. You could have directly done /bin/sh, and you could have gone into the shell of the container. or you can directly run that command that you want to run in that exec itself without getting inside the container using the shell. Right? So once you've explored that, can I have a raise of hands if we can proceed? The next thing we want to do is test this. Once this volume share works, the next thing we wanted to do is actually connect to this Nginx container or Nginx pod that runs these containers and see if I can actually connect to this as a client, right? So in the same pod example folder, we have a client netshoot.yml that's running, right? So what this YML basically does is it starts a netshoot pod which runs this netshoot container, which can be used to access this other Nginx container that's running inside the other pod, right? So there are two pods and you want to see if these two pods can communicate with each other. So similar to what you've been doing till now, before doing that, there's this step that I've added that open the client shoot.yml and you have to edit it. So what it has is, needs to have the IP of the pod that's running the Nginx container, right? So how you get the IP is, kubectl get pods, we're getting QC, right? If you do -o byte, you'll see a IP column running there and you'll see a IP there, right? Pick that IP and replace it in the section that's there in client shoot.yml. Right, so there is a ping and after that there is an IP in that file. So replace that IP with the IP of your Nginx container that's running, Nginx pod that's running. And to do that, use this command. Once you replace the IP in this YML, in the clientshoot.yml, apply the clientshoot.yml using this command. Similar to what you've been doing till now. So if you are able to exec into this new netshoot pod, what you can do is do ps-e. So what it does is, if you open ps-e, you will see the first process with the PID1, it's running a ping. And that ping is going to the IP that you just edited it, right? And that IP is the Nginx IP, Nginx pod IP, right? So this is the first sanity check that if you are able to connect or not. So how are we able to connect is what we will cover tomorrow, but it's what the underlying Kubernetes infrastructure takes care of you, where it assigns IP addresses to your pods and they can connect to each other using this cluster IP that gets assigned. Right? So if you are able to see the ping working, right? So next thing that we can do is check if that service itself is being able to connect, right? So remember when we created the Nginx pod, we exported the container port 80, right? So it should be, when you hit that port of that Nginx pod, you should be able to get some basic output back. That's the first I'm working message that comes when the Nginx pod is up. So what you do is, inside the pod, just do a curl, and this Nginx IP is the same IP that you just put in the client netshoot command, right? So that ping with whatever IP you gave, that same IP you use here as the Nginx IP, and then :80 is a port that's open for the Nginx container, and you should get a HTML page back saying the Nginx pod is up. So now you've seen that you have to hardcode that IP to connect to this pod, right? So next we are going to see is what is called, as we mentioned earlier, the init container, right? So what this init container does is, it tries to create a volume, and once the volume gets created, then only start the Nginx pod that's running. Right, so there is an init test.yml that's running. that's there in the pod example. Apply it, and once you apply it, immediately do kubectl get pods, and you will see the status of the pod that's coming up. And it's different from what you get running. There is a slow process in which you will see different stages that go into before starting the pod, because it's waiting for the init to be up. The 0-1 implies the init container is still checking. Right? Once it becomes 1 on 1, that means that init has completed its process, it's up to good, and it's trying to initialize the pod. So the first state you will see is the init 0-1, and once it becomes 1-1, you will see the pod initialization for the Nginx container. When you deleted your container in the morning, did it restart itself? What did you have to do again? So if you are running your application on a cloud, if it stops, is it a good sign that your application stops and there is someone sending requests to you, or you want it to be on all the time? Right? So you want your application to be running all the time, and that's the whole need that you spend your time making their application to run as microservice to be running on the cloud. Right? So you want it to be up all the time. So is it whose responsibility it is to keep that application running all the time? Is it the application developers or it's someone else's job? Sorry? Right? So it's the infrastructures or the orchestrator's job to take care that as an application developer, you don't have to worry about if your pod is going down or your service is going down because of some resource issues. It should be the orchestrator's job to make sure that your application is up all the time, right? And it needs to be done without the application developer or without you knowing about it, right? So how do you ensure that in Docker containers? Is it possible? I need some answers, guys, or a bit more loudly as well. Is it possible in the Docker container to make sure that your application stays up all the time? No, because you have to manually start, stop, and manage them, right? So you need, that's not possible in Docker container. So that's where the main contribution of Kubernetes comes into play. As an orchestrator, it takes care that you don't have to manage it coming up and down all the time. And how does it manage it? Did it manage till now? Like all the steps did you do till now? If you do a kubectl delete of the Nginx pod that's running, will it come back up? Why? Because the pod, yeah, you did not set up anything to make sure that it comes up. So what do you need to set it up? Right, so what you need to set up so that...
Guys, more interactivity, please. What are you doing? Answer, come on. So, yeah, so just to kind of stress the point, right? So, Priyanka mentioned pod is going down. So, I want some answers on why is the pod going down. I want at least 3 answers. Somebody answer. Anything? Okay, we have one answer out of memory. So, something was running in the pod and then it took more than it's supposed to. Got deleted, right? Good. Okay. Some other answers? Some guesses? Hardware overloading. So good. It's a good one. So the pod is running on some particular system. Maybe something else happened on the system and it kind of crashes. Right? That's good. Right. So these are kind of reasons why, for no reason, for no reason of the application developer. Right. So application developer didn't really think about this, but it can still happen that a pod is dying. Right. But in today's example, we just showed the pod is dying. But do application developers want that? No. They want it to be running. Right. So that's what Priyanka has been talking about. That we need a system to be actually having active pods, even if they die. Right? It's okay if they die, but they have to start again. That's where.
Yeah. So in Kubernetes, who takes care of it is what is called as the deployment, right? So when you create a deployment, you run the pods inside the deployment. It makes sure that if it goes down, it keeps coming up to the number of replicas that you've asked the deployment to run. Right? If you've asked for 3 replicas to run for that application as part of the deployment, as we see in a while that we will just now run. It makes sure that at any given time, 3 pods for that application run. Right? It will make sure that's the job of Kubernetes, and that's what the deployment will take care of. Right? So even if you try to delete one pod, it will still make sure that if you physically delete that pod using kubectl delete, it will still make sure that the pod is up all the time. Right? So let's try with the help of an example. So this is a meme that we saw online from one of our friends, that how do you make sure what hierarchy it is, right? So what you started in the morning or what you're doing till now is the container, right? You had the smallest unit of where your application was processing, right? So then we moved on to saying, okay, I need someone to manage all the networking so that it connects across network, connects across clusters, gets deployed on the cluster. So you wanted to move to Kubernetes, where you started running it as a pod, where you can actually run more than one containers as well, right? So you got to the pod hierarchy. Then you wanted to make sure that the pod has, your application has a certain number of replicas running, right? So there is a replica set that internally deployment assigns. When you open the environment, you will come to know there is a replica set that gets created for you to make sure that if you have asked for 3 pods running, it makes sure the 3 replicas are running. Right? So this is the hierarchy, that is deployment requires make sure the replicas are up. What runs inside the replicas are the number of pods that you've asked for, and inside each pod is finally the Nginx. For in our example, the Nginx application or any application that you wanted to create to be running. Right? So let's explore in our environments, does deployment really work as it's supposed to do? Right? So what you can do is, there is another folder in Kubernetes called as deployment example, deployment underscore example. Can you go in that folder, please? So in that folder, there is a nginx deployment.yml. Can you open it up for me? Okay, so if you go inside the Kubernetes folder, there is a deployment.yml. Can you open the nginx underscore deployment.yml? So what is different from the nginx underscore pod.yml that you just ran earlier? Do you see any difference here? Yes. You have the replicas here, which says that I want 3 replicas of the same nginx container that we had created earlier as a pod, like just single pod. It is telling you that I need 3 replicas to be running for that. Right? So that's where deployment will help. Right? So what we want you to do is apply this deployment in the namespace that you just created. Can you do that now? Now, once you, in case you've applied it, just do again kubectl get pods and see what you get. Yeah, if you have some older examples, is the delete working for everyone, or are they facing some issues with the delete?
Yes, it's working.
They are pending. No, there's no. The old one. Yeah. It is pending because of our proof. It is shared and init test. Yeah.
So this is actually a good, it happened accidentally, but it's nice to show you, right? So you are able to see that you reach some kind of limit on the cluster, right? And this is not the CPU limit or memory limit, because for none of the pods we actually asked, like, I want the CPU, right? So this is actually just a number of pod limit, right? This is yet one more control that Kubernetes is giving, and there might be ways to actually change that to a larger number, right? Because we have enough CPU memory in the cluster. None of you are using that much that it's actually loading the nodes, right? But what it's loading is the Kubernetes control plane, which is being told that you can only run so many pods. So if you delete the older pods, you should be able to like free up that quota, and your newer pods should be able to go, right? But this is like we are in this demo cluster, we have one node, right? But in real clusters, we have hundreds, thousands of nodes. So one node might obviously run out of space or run out of quotas like this, which is perfectly fine because other nodes are there to pick up that slack. Right? So that's how the clustering will. That what you see if you run a describe, you can actually see that while it's in a pending state, it will say Kubernetes scheduler is unable to find a node to place. Right? In a real cluster, it will go to the next node, next node, next node, keep searching for a place, and it will only fail if all of your 1,000 nodes are out of it, right? Which is very unlikely situation.
So once you deleted the old pods, are your deployment pods, which have the whole text after that name, are they coming up? Are they running now? Okay. So if your pods are in the running state, I'll ask you to delete one of the pod that just got deleted, created because of the deployment, and see what happens.
So this pending state that you see is also a demonstration of Kubernetes abilities, right? Like you are asking for a pod, the deployment is asking for the pod, you have not got it, but it doesn't mean that Kubernetes is going to just give up, right? So it will keep retrying with some time mode, with some default time mode. So it will keep retrying until it gets that quota. So some of you will already have deployed EC 3 pendings. Now if you just do kubectl get pods again, you will see some of them have gone and running, right? So this is yet another, the core, what is known as the core loop of Kubernetes, right? That looks at what is the current state, it looks at what is the desired state, and it tries to go from the current state to the desired state again and again and again. So the desired state in this case was 3 running pods, but the current state is 3 pending pods, right? So that's it.
So once you delete, what did you see?
शेयर वॉल्यूम टेस्ट करना रहने दे ये वाला
The deployment done for you. I just bring it down.
Can someone answer what did they see after they
like
deleted the pod?
Now delete the deployments and other people's pods get.
And is the ID matching with what got deleted?
They deleted them.
No, right? It creates a new pod when an old one gets deleted, but it makes sure that whatever number of replicas you asked for in the deployment are there at all.
Pod named after the first one.
So is everyone seeing the same thing? Did they delete one of the pod that was being created by using the deployment environment? And were they able to see that it's restarted, like created a new, did not restart, but it actually created a new pod for you? Okay, so if you could see your pod restarting, I think in the interest of time for the rest of the slides, we go over just the content and maybe offline if you, as you are in this campus, tonight you can try the rest of the commands that are there in the slide PDF that you share on Slack, right? So the next thing that we wanted to talk about is config map, right? So how many times does it happen that you guys can have you all here? We'll just cover the theory of remaining sections that we wanted to cover today. Okay? So, how many times it has happened that you've written an application, configured something, and wanted to change something in that configuration? Right? It happens most of the time, right? So, what will you do in case when you are running a production grade application on a cloud and want to suppose change the configuration for it? Look, I'll give you a simple example that we faced like last week back, right? So we had a sidecar running for our container, which was monitoring that container, right? So what we had told it was we wanted to connect 10 metrics for our container, right? So it was connecting for us. But then we realized that we were facing some issues and we required it to not send out 10 metrics for us, but send out more than 10, like 20 metrics for us to be sent because there was an extra metrics that we needed to debug some issue, right? So what would we have done? We would have to stop that container or stop the deployment because if you stop the container, deployment will restart, right? But like re-add that pod. So would we stop the deployment, change the configuration, and start for it to expose 20 metrics for us? No, right? So you cannot do it. That's whole point of being available in a Kubernetes or the cloud infrastructure is you do not have to bring down your application each and every time you want to change something, right? So that's the whole point that support that config map provides. That is, you don't have to restart your pod every time you want to change your configuration. You can provide a config map which will get mounted as a volume in your in your pod, and whenever you change any configuration in that volume, it will automatically get updated in the pod without you worrying about it. Right? So if I had a configuration saying number of metrics colon 10 in a config map that got deployed, I just changing the config map to 20 would have actually did not restart the pod, but actually enabled 20 metrics to be exposed by that pod. Right? So that is the support that config map provides. Just to know that you cannot consider it as a standard volume that you want to create or you store your data because the max size that config map can support is 1 MB. It's just a key value store for you to give configurations to be changed on demand. Right? So we'll skip this part in the interest of time, but I request you guys to just go try it out on the namespace that you just created and see config map in action. So what we'll show here is the Nginx that was running. When you did a curl, it actually printed out a home page that way, right? And this config map will take care of updating that home page to something else that you want, right? So this you have to follow these steps here, edit the config map that's there, or just follow the steps here, and when you redeploy or in that same pod, if you apply this config map and you run the curl again, instead of the home page that you got earlier, you just get get Eureka, because that's what I've asked the config map to do. Right? So you can see that once you try it out. The other thing we wanted to tell you guys is, okay, we saw that deployment took care that number of replicas that you wanted stay the number of replicas you wanted for that application, and number of it they kept running, right? But what will happen is, what if I want just these Nginx application that you run right now is a stateless application. What do you mean by stateless application is, it doesn't store any state locally in that pod, alright? There's no volume that was wanted to that pod, right? So if it goes down and the pod gets deleted, there's no state loss for me, right? But most of your microservices chain or whatever application you build has a database or some microservice running that needs some state to be stored, that needs to be persistent, right? And it needs to be persistent across restarts of the pod, across, like, as you saw when you created a deployment, a new pod got created. If it was just a deployment and it had a volume mounted on it, you wouldn't have been able to access that volume, right? But you wanted, but if it's a database, you don't want that. Even if a new pod comes up, it should start at the state with the state that the older pod got crashed in, right? So that state loss is not acceptable for microservices like a database application, right? So these stateful steps take care that even if you go down, like your pod goes down, the state is maintained across your restarts, right? So we'll see a stateful example in a bit, right? So before that I spoke about what is called as, I want the state to be available even after the pod restart, right? So how do I maintain that, or how does Kubernetes allow you to do that? So it allows you to do that by creation of a special resource which is called as a persistent volume, right? So with persistent volume, what it does is, it creates this persistent volume it mounts it on a node, but it stays, this persistent volume doesn't get deleted even if your pod restarts. It stays there till you go physically and delete that persistent volume, or if the node goes down, right? So if the node goes down, the persistent volume will go, but without that, and unless you delete it, the persistent volume stays. So if you have an application connected with the persistent volume mounted to it, it will take care that even if the pod gets deleted, the persistent volume stays across restarts, or your state stays across restarts, right? So how do you claim it? So this persistent volume, so you create a persistent volume claim to amount of disk that you want for your pod or your application to be running, right? So there are examples for it in the folder in the Kubernetes that which is named according to it, and you can go and try it out in your free time. Right? So stateful set, as said, it needs a persistent volume. So each pod that gets created in the stateful set has its own persistent volume assigned to it, right? So that there is no concurrency over it. Like, if we don't want both the pods riding on the same state, so each pod that gets created as a stateful set has its own persistent volume created. Right? So there's some examples for you to try out later. Other set of we've studied about deployment, we took care of replicas, we spoke about stateful set, which took care of the state that needs to be there for our application like a DB. But there are some other special pods that need to be up, right? If I want to run something on each node of your cluster, right? For example, I want to collect logs or collect metrics of the cluster itself, because you can expose your metrics for your application, but you need to see if your system is up, system is running correctly, each node in the each worker node that's there in the cluster is running correctly, there are no resource bottleneck, as you said, right? You guys had the pending state for your pods, so I want that to be also given to me, right? So I need something running on each of these worker nodes so that it gives me the data back. So there is a special type type of pods that you can create on these worker nodes, which are called as daemon sets. So daemon set has an instance of pod that runs on each of the worker node that's there in the cluster. And there's no, like when you create a deployment, there's no guarantee on which node it gets created on, right? It can happen that one node can have two replicas of your Nginx pod running and another one did not have anything running. But if you create a daemon set, because we want some special operations to be done, it makes sure that you have a pod running on each of these worker nodes. So example for that, as I said, was collection of a pod on each of the daemon sets. So what we had was that we had a two cluster environment in our local environment that we had. We had two worker nodes running in the cluster. We had two replicas of the daemon set running, right? And both of them, as you can see, the node here, right? These were the node names of the physical server or in that were part of our cluster. Both of them, on both the worker nodes, we had this fluently pod deployed because we created a daemon set to create this fluently application, right? Fluently is basically a simple application to collect logs for your environment, right? So this application was running on each of the worker set, and what we did is we added a new worker node to the cluster, right? We wanted to scale the cluster to add more resources, and you could see that immediately after we added a new worker node to the cluster, the daemon set, because it was a daemon set, it made sure that we have the fluently pod running on that new node as well, right? So these are different types of uh, uh, ways in which Kubernetes takes care that you scale your application well, your application is highly available, monitored well across all the worker nodes or across the cluster on which your application is running. And as well as make sure that even if your application is stateful, we maintain the state for you. That's what Kubernetes provides you with all these things. Right? So last thing that we wanted to touch upon, which we will cover in detail tomorrow, is services. Right? So remember when you created the Nginx pod and you wanted to ping it through the Netshoot client, right? What you had to do is go do get pods, get the IP, come back, edit that pod, and then try if the ping was working, or just curl the IP and take that IP and the curl, right? That's cumbersome that way, right? If I have 100 applications running, I can't just do get pod for all the 100 applications running and just keep on editing and adding that IP everywhere, right? So you need some abstraction so that you can easily connect to these pods that are running. So what Kubernetes provides you to do that is with the help of services. Right? So what service helps you to do is, once you create a service that comes before a pod, a set of pods suppose, you can directly hit this service and you don't have to keep handle of all the IPs that way, right? You had just one pod, you can add it. But if you had a deployment now, right? You had 3 replicas. You can't just go about and replace that IP address every time in your ping or in your curl to make sure it goes to that backend node or backend Nginx that was running. And also that won't handle what is called as load balancing, right? It won't handle that because you are manually doing a curl to that particular IP address. It will make sure that your curl goes to that IP address itself. So if I have 10 clients running, they make sure that they hit only that IP address, and even if that pod is up, they won't be hit. Like that IP won't be hit because you manually change that IP address to be that other pod IP address. Right? So you don't want that. You want seamless connectivity, seamless management of which request goes to what pod when I scale. Right? If I have 10 replicas, all the 10 replicas should get the request. That's the whole point of scaling that Kubernetes will provide. Right? So that all is supported with the help of services, where you expose a pod or an application that's running as a pod, as a service, and you can just hit this service, and internally Kubernetes takes care of that which pod it hits and how it hits these requests to these pods. Right? Seamlessly, you don't have to worry about it. Kubernetes takes care of it. If it was in the case of Docker, you couldn't have done it because there's no service abstraction that exists in Docker. You have to go hit your, or you have to go create your own load balancer and make sure that it maintains whatever backends it has. Like it maintains the IP address of all the backends. Make sure that it load balances to these nodes as well. Okay. So there is some environments that I wanted you guys to try on for this service as well, but in the interest of time, we'll stop there. So to summarize, what we saw today was we created, as part of this session, we connected to a Kubernetes cluster. We created our own namespace, created pod on it, and we saw that it couldn't scale, and we couldn't. So we required something to help us scale. So we created a deployment so that we could scale and manage the number of replicas that are required for the application. We saw that we could also maintain a persistent state for that application using stateful sets and persistent volumes. We saw that you don't need to maintain the configuration, like you can dynamically update a configuration using config maps, and also you don't have to maintain the IP address or manage how the load balancing happens for these pods. Services does that for you. So that was what we studied in this session, and I know we couldn't get to all end of it, but this was just one application that you ran, right? You just ran Nginx. In the morning you ran Nginx as a container. Now we ran that Nginx container inside a pod and Kubernetes, right? But it was just one single microservice running. But in real life, you have any number of microservices running if it's a Uber application or if it's an Amazon application, right? So just to get a feel of how these microservices get deployed and how they communicate with each other, in the slides we have a link to a standard application, the example that I kept talking about, where you have a front end and you have a Redis data store running at the back end, and you want to communicate with each other. You want to use the stateful set. You want to create a persistent volume to get the actual feel of a microservice tree. This is a real world example that we have given at the end of these slides, and you can go there and try it out to feel how these things are working. Right? So with that, we'd like to end the session for today with a quiz. Right? So quiz on what you studied today, right from what's virtualization, what's containers, how you create the containers, how you manage the containers on a single node using Docker, how you help them being deployed on a cluster, Kubernetes cluster. Right? So I'll share the link on Slack. Okay, so Kavya is sharing the link to the form that you have to give the quiz in. Right? Just to get sense of where we are, what we understood today, what more we need to learn. And obviously you have the slides for today, you can go back, refer to them, come back with questions for us. If you try the commands that we couldn't finish today for Kubernetes and Docker as well, and some of the namespace things that we couldn't try hands on, you can try that out and come back.